Okay, we'll get started. As people continue to log in, they'll catch up. But first, I want to thank everybody for taking time out of their day to join us for the Design Professional debut online this month. We are going to continue our best practices theme and cover chapter 6. But before I get started, a little bit about myself. The presenter here is Chad Julius. I've been with Allen Block for almost 18 years on the engineering side, so get to see a little bit of everything, and that's the best part at Allen Block Corporate on the engineering side is we get to get exposed to the good, the bad, the ugly when it comes to retaining wall designs, and we get to do walls every day, as fun and exciting as that sounds. So we do enjoy this part of it where we get to share the knowledge that we've seen in the past and kind of things that have worked and where we've seen some struggles. So what I wanted to do is just outline a little bit about the best practices. We talk about what's next and what is best practices. Best practices is that industry initiative. I've got a couple attachments as part of this webinar, and one of them includes the complete document of the best practices. So feel free to download it at your convenience, or even our website has always got access to it whatsoever. And what you're going to find is that document is easy to navigate. So you can search for the table of contents, and you can quickly find the information you're looking for, because it's pulling it through or pulling information from our spec book, from the commercial install manual, from the engineering manual, from industry experts. Like I said, this is an industry-wide initiative kind of centered on that best practices to make sure you got that zero wall failures. And so the NCMA, which is the National Concrete Masonry Association, they've got a version of the best practices manual out as well, and it's very similar to what we have. So feel free to reference that, but it's especially when it comes to chapter 6, soil and compaction, there's not a whole lot of differences. And really the reason why best practices was born and developed back in 2015 is we wanted to avoid wall failures. We saw far too many problems out there associated with not only construction, but also design. So we wanted to try to bring some information, kind of that common sense approach to this. And we also know that designers, there's that delegated design option where it's designed by others. The site civils will do a great job of recognizing when a retaining wall is needed, and they'll put a line on paper and even call out the top wall, bottom wall geometry, but they'll say designed by others. And others usually means the contractor has to go secure that engineering. And a lot of you guys do that, where you guys will work with the contractors and help them provide that solution to that engineer drawing. Now, the problem with that is now that's that communication. You got to back and forth, maybe with different submittals. And so we try to minimize delays and eliminate oversights by having the design of that retaining wall go out as part of the design documents. And that way, hopefully you guys are either doing it in-house or working for the design team as you go through this. So there's a lot of reasons why best practices exist. And as you know, some of you guys have joined us over the months. We're going through each chapter almost one by one. And Logan, an engineer here with Allen Block, did chapters 3, 4, and 5 last month, and it's all focused on water management. In fact, we spend a considerable amount of time on water, because we know almost 60% of wall problems out there today is because of improper water management. And so some of the bullet points that you're going to hear throughout this presentation is making sure we drain water away from the walls and not over the top, and make sure if there's any excess water, whether it's through irrigation or natural sources, we're providing the path of least resistance and getting it out away from that soil and that infill area. So we're going to build off of what we learned last month for that soil and compaction. And so this month, it is all about those two topics. And in my experience over the 18 years, it is really the next two reasons why we see problems out in the walls. One, with that soil, and pretty much it has to do with the overestimating or even assuming the soil parameters that are being used. The design calls out for one thing, but then you get to the job site and it's completely different soils, but nobody catches it or nobody changes the design to account for that soil change. And then the other one is compaction. We know compaction is critical. It minimizes the settlement and any problems that we have, particularly right at the face. And you'll hear me talk about that too when we get into compaction, because it prevents those down drag forces. And what I mean by that is the geogrids are meant to be horizontally through this wall starting at the block and going into the hillside. Well, if the soil settles but the block doesn't, you get those grids that are forced downward behind the block, and you could actually overstress at that point, and those down drag forces could be a little bit of a problem. So a lot of times we see people consider compaction as a construction issue, but I would challenge that we could actually, on the design side, be more proactive by calling out the specified requirements, whether that's the level of effort or the testing. And we'll get into that a little bit more. I should note that I do have everybody on listen only mode. So if you do have questions, feel free to use the question option there, and I will try to do my best to monitor that throughout the presentation. But if I do miss it, rest assured I got some time here at the end of the session that we'll address every one of them that's been asked. So just keep that in mind as we go through this. So I have to get started with the basics. The whole soil and compaction chapter of best practices has a lot of different references to types of soil and plasticity indexes and compaction levels. So I thought I'd take the first part of this ABU Online and really talk about the soil mechanics. Now, I know I've got a number of geotechnical engineers that do this for a living on the session here, and so this is kind of a broad brush, high level item for that we're going to go through, and I don't want you to think that this is the end all be all, but some of the things we're going to talk about is obviously the testing side of it. What does that mean for grain size, Atterberg limits, classifying those soils, even the boring logs and testing and stuff like that. So when we get into this, you got to start by classifying the soils, and a lot of it starts with the grain size. I know we've got some international attendees on this call, and I appreciate that. And every single classification might be a little bit different, but it all has to do with some type of a particle size. And so this is a picture of a sieve analysis where they're shaking the different pans, and it starts with larger openings on top and goes all the way down to the pan size on the bottom, which is 0. And you just shake that over a period of time and collect how much of that original sample is collected on each one of those sizes. And then you just simply graph it. This is sieve analysis results where you've got across the top there the size of those particles. You got boulders on the left-hand side moving all over to the gravel. You got coarse, medium, and fine, kind of with that sieve analysis. Then you got sand, coarse, medium, and fine. You can see the coarse starts at number 16 sieve going all the way down to a number of 100 sieve. And what that means is a number 100 sieve has 100 openings per like one square inch. And so very, very small. You'll see the silts and clays really start to come into play after that number 200. And that's what we consider a fine material. And all we do is with that grain size analysis is just shake it and find out how much is passing that, and that's what's being plotted here. So these two samples that were tested are being plotted, and you can see that most of it ends up in that sand category, which makes it pretty easy to identify that is going to be that sand particle is what they've identified here as well. So once we know the grain size, now we need to look at the Atterberg limit, especially when you're talking about those cohesive soils, those tight soils where you've got the clays and silts, because not all clays are obviously created equal. And so we really need to identify the plasticity index, and that just measures the range of kind of how plastic or how moldable that water, that soil is, because it's really temperamental when it comes to water. It has to do with fat or lean clays. And I should point out that these Atterberg limits, I've got a handout also attached as well. It's our technical newsletter that was number 19, so a couple years back. But these newsletters, if you haven't been seeing them, we send them out once a quarter, and I think we try to do a pretty good job where we highlight a particular project, but then with that project we give design considerations and construction considerations, and those are every quarter. Those get sent out, so I hope those are hitting your inboxes and you're finding them useful. But technical newsletter number 19 specifically talks about these soils and what are Atterberg limits, and I took some of the information from there, and some of you guys live in this world, but Atterberg limits are defined, at least here in the States, with the ASTM D4318, where you have to define what the liquid limit is and then the plastic limit. And there's a couple different tests that can do that. I'm showing two of the most common ones. The liquid limit is using the Casa Grande cup, where they just go ahead and cut a groove and then count the number of blows that it takes for that groove to come together. And they do that over a different series of moisture contents to find out that liquid limit where it behaves more like a limit. Some of you guys are international and you might be more familiar with what they call the fall cone test, kind of a little bit more common in Europe specifically, but it's just still giving you that moisture content of that limit, liquid limit that is. Plastic limit, all they try to do is take that sample of soil and roll it out and try to get to about 1/8 of a diameter or 3.2 millimeters. And obviously, if you cannot get your sample to get to that narrow bead, then it's not lit plastic at all. So we do those two different tests and we find those moisture contents to allow those to happen. And then a plasticity index, PI, you'll hear me talk about it quite a bit, is just the difference between those. And so a point of reference is for most soil classifications, anything that has a PI greater than 50 is really considered that fat clay or highly expansive or plastic. And those are problematic. In fact, most of your engineers, geotechnical engineers, will say that anytime you've got those very fat or plastic clays, we don't want to use those in construction, and definitely we don't want to use those in retaining wall construction. In fact, when we go on and say, when you got those highly expansive clays, whether they absorb moisture or even on the flip side, could actually collapse, creating some settlement because of it dries out, because that's how sensitive it is. We don't want to use that for construction. In fact, the allowable that we say, and we'll get to this a couple times today, is, we want a PI less than 20 and a liquid limit less than 40. Best practices goes on to clarify that a little bit more. Again, best practices, that zero wall failures initiative, we go ahead and say we want that less than 6 and less than 30. So there's a lot of things that go in with that. But once we know the particle size and the kind of the plasticity index, especially when you're talking about the unified soil classification, you can go ahead and qualify the type of material you have. Now, there's different variations of this. I show this here, and even different countries that we have on the call use different versions, but they're all basically routed in the same options, which is the soil size and properties. So here, this is the USCS, just kind of a little bit of a summary. Obviously, it starts at the top with the larger material with the gravels. You can see that you've got different types of gravel. The GW is a well-graded granular material. GP is poorly graded. GM's got a little silt. GC's got the clays. Same thing with the sands. You can see we got the SW and SP. SP, if you ever see that on your site, that's got to be something you gotta watch out for. That's the poorly graded sands, like your sugar sand or your beach sand. We'll get into more of that too. But then you get down into your clays, and you'll see with clays that Atterberg limit, that liquid limit, really comes into play here a little bit. And so if you got ones that are lean, that's where the L comes into play. If you got ones with the H's, that's that heavy clay. Those are the ones that are being classified by the higher values there. Right? So just keep that in mind. Like I said, there are many different classification systems out there, but they're all rooted in the same option here. A couple other things that we wanted to talk about is the actual grabbing of these samples, the exploratory drilling or test pits or whatever. I'm going to go on with the borings. And I always joke because doesn't mean they're dull or not exciting. We're using some type of a hollow stem auger to kind of get to the different elevations. But once you have the samples, then we just go ahead and run the different tests. So we can classify the soil, we can grab the moisture content, we can get an idea how stiff it is with the penetration numbers, and then we get back into that water elevation again, building again what Logan emphasized, that if you've got a hole, we can measure the water elevation if there is one in the hole, and find out if we've got a perch table or that's something that might cause problems in the long run. So it's all identifying those potential water sources. But the only way to do that is through exploratory drilling. And here's a kind of a summary of it. Here's a log that summarizes that bore. And if you look on the right-hand side of that, you'll see the number of blows and the moisture content and the dry densities, but those correlate with the sample that was collected. And so you can see they grabbed 3 different samples within the first 6 feet, but then they went 5-foot increments after that, and you get an idea of what type of material you're working with by doing the classifications. But I often stop here, especially when I'm working with our producing partners and our contractors out there. A lot of times, even engineers want some assistance from Allen Block Corporate, which we're happy to do. We're happy to give some technical assistance, do some preliminary design work, go through it. And it often makes me laugh when we get 50 pages of boring logs in a geotechnical report, because if you see this is great. It might give you a broad brush stroke or a broad brush view of what the soils might look like, but it doesn't really give you the shear test, the friction angle, unless that's being under like the other lab reports. So like I said, to really get the values that we need, unit weight is important, but then the shear strength is even more important. And that's done through some type of shear testing. There are two different ones that I'm looking at here. You got the direct or the triaxial shear testing, and really the difference is night and day, to be perfectly honest. Direct shear testing, you get into it's simpler, it's faster. You can do that a little bit within the budget. Triaxial is a little bit more involved, but generally most people agree that it gives you better results. And a college professor of mine often referred to, what are you looking for? If you're looking for shear at an angle, 45-degree angle, which is a lot of times how soils fail, triaxial shear might be a little bit better. But if you're looking in the horizontal plane, direct shear might be better. But really, it comes down to the time, the scope, the budget. Gets into the geotechnical engineer's expertise. Either way, what we need to get is those shear testings need to be completed so we can get the friction angle. And those of you guys that have done retaining wall designs understand the friction angle is one of the most important, because it gives you the strength of soil. It determines the K sub A value or the active pressure coefficient, so you can determine how much pressure is exerted on that wall. So shear strength is so important. And if the design team is all up front, these can be budgeted as part of the scope of work for the engineering, as opposed to, I know some of you guys work for the contractor. That means you got to go back and ask for the test after the project's been bid, and that can be problematic because the timing doesn't work for you, and neither does the scope work for you. So that's why we like best practices, trying to get a lot of these tests done, getting these geotechs as part of the design team to give these values. The last test I want to talk about is compaction. Obviously, this is soil and compaction. One of the ways we get the compaction is through a Proctor test. And really what that is, that's giving you the moisture and density relationship. And there are different Proctors out there. Most of you guys are aware of this. When the Proctor originally developed this option, it was the standard Proctor, and that is ASTM, ASTM 698. And that is the time tested, where you've got the 3 different lifts, 5.5-pound hammer. But then the modified was developed because the Corps of Engineers were having problems with rutting on airfields and stuff like that, and needed a test that was a little bit more robust. And the modified has another ASTM standard, 1557. So both of these are well documented. And it is interesting. I notice modified versus Proctor, there's a lot of debate. Some of it's regional, really specifically here in the U.S., the western side of the U.S., especially in up and down the west coast, where you have the seismic zones. Modified tends to be more used, but standard is Midwest and East, where we don't have those same dynamic loadings. But modified, anytime I've got a loading or surcharge roadways, that kind of stuff, I tend to look at that way. But I always kind of relate it this way. When I was, again, going back to schooling, I had a professor that says, hey, you have to know the modified Proctor because that is the new test. It's going to be accepted. Everybody's going to be using it. And then I kind of relate it back to when in elementary school, we had to learn the metric system, meters, inches, or meters versus inches and all that good stuff. But here in the States, we still drive in miles per hour, which means all that tells me is we don't change very quickly. And so that's why I see, you'll even hear me refer to the empirical units or the English with the feet and inches, and I'll try to bring in the metric as well. But that's why we see this divide versus standard versus Proctor, standard versus modified. So again, we always go back to the local geotech, have their experience, their knowledge. They know what's readily used or more often referenced in the markets, and so we tend to look at that. I do point out the difference because standard Proctor is what is typically referred to in the retaining wall market, and they're not the same. Obviously, if we're calling out for a 95% standard Proctor, that is not equal to a 90% or 95% modified. In fact, the University of Nebraska did a study, and they say it's anywhere from 3, 4, or 5% difference depending on the soil samples, but they can range quite a bit. So just keep that in mind. All that does, though, is the Proctor test gives you that soil density relationship. So here's that curve where you do numerous tests over different friction or moisture contents, and you're getting that optimum moisture and maximum density that's being reported. Like this sample's at 116 and 10.5% moisture. So just something to consider. But here, that was my soils review. Hopefully some of it was a review for a lot of you guys. Maybe it was new for some of you, but we're going to emphasize throughout this session that soil properties can't be overlooked. We know they're critical when it comes to wall calculations, even global stability, which we'll be covering here in the next couple months as far as additional chapters for best practices. And the only way you can get those testing the values is through that geotechnical testing, and so we can accurately determine those soil properties. So again, no questions so far, which is fine. But again, send those questions in as you get it. I'm going to transition to what we actually find in the best practices manual, and it's going to build off of the knowledge that we just gleaned from the review here. Again, best practices, quick, easy references. It pulls from spec books, commercial install manuals, all that stuff. So all I'm going to do is you're going to see a little bit of redundancy in some of the talking points, but it highlights different aspects of the soils within and around the wall structure. First one, we talk about what is allowable, what kind of soils can be used. One of the big advantages of segmental retaining walls and Allen block is that more often than not, you can use on-site soils. That saves money. You don't have to bring soils in. You don't have to haul soils off. And so if we can use the on-site soils during the construction process, that helps. And that is key because that can only happen if you are handling the water properly, or if you've got compaction there as well. And so there is huge emphasis, and that's why we come back to chapters 3, 4, and 5 for that water management. In fact, this cross section you see here is just from our software, AB Walls 3D, where it's showing some of the changes we made to our software based on best practices. Here you can see we've got a chimney drain on the back using a geotextile or a geofabric. That's plugged into some type of a heel drain. Then you've got a blanket drain, which is nothing more than the same rock that's being used at the bottom. Obviously, there's material between here or a swale above. So we're showing ways to grab that water and not have any problems when you have soils. More often, site soils have that clay content, are less likely to change their properties when they maintain their optimum moisture condition. We do have a question that says, talk about the plasticity index change in response to rain events, and how do you deal with that? Rick, this is exactly timely. You try to prevent it. You try to minimize how much water is being introduced to that soils. So that's where these blanket chimney and swales, all of these are being added to the system to keep your soils here as optimum as possible. And so we'll continue to elaborate on that as we go through this as well. But we know cohesion-less soils, your granular material, obviously with plasticity index greater than 6s or less than 6s and stuff like that are great. But when we do have those clay materials, that range of plasticity index and stuff, we need to make sure that we've got that improper drainage, as we just talked about here. But then other things to consider, frost. In the northern climate, especially where our corporate headquarters is in Minneapolis, Minnesota, our frost depth can be, 5.5 feet deep. And I'm not so much worried about heaving up and down as opposed to maybe some bulging where you've got frost susceptible soils right behind the wall. That's another reason why we use that clean stone, at least 12 inches there, to try to prevent any kind of that swell or that heaving. And there's times when we got to make sure that's done properly too. So if you got real frost susceptible soils, you might have to increase the amount of rock you have there too. Little note on allowable soils, we talk about cohesion. Cohesion is that soil property about basically how well everything kind of binds together. I always kind of remind everybody that cohesion is water soluble. So in our industry, we tend to ignore cohesion, whether that's for external and internal analysis. We do see cohesion jumping in on your bearing capacity calculations. We do see it in global stability calculations, but even then, you'll see it in best practices as we recommend using only a certain percentage of the tested value. We say no more than even 10%. We know that's conservative, but we also have seen far too often where walls are banking on that cohesion to help keep that soil stable, and then all of a sudden a little water is introduced and that value is no longer there. And then the last point when it comes to the allowable soils is obviously when you're talking about that heavy clays, that high plastic material, that can't be used. And so plain and simple, we just remove that, then you are going to be using some type of a select backfill. Okay. 6.2. This is understanding your site soils. Plain and simple, we just need that geotechnical engineer involved. We need that on-site soil, making sure we've got material that's been covered. And this is really kind of getting into more of the subsoils more than even the backfill. Subsoils, to me, is probably where the most assumptions are made, where we got a better idea what the backfill material is going to be, but then we just scratch the surface because we don't need a concrete footing here. We scratch the surface and then we just start building a wall. Meanwhile, we could have been building on some fill, a marsh area, some wetlands. We've even seen guys built on cars and trenches and stuff like that. So understanding what's below grade is so important. Again, I'm taking a page out of our AB Walls, our design software. More often than not, the leveling pad is just simply 6 inches by 24 or 15 centimeters by 60 centimeters. But if you've got poor soils, there's absolutely no reason why you can't just expand that leveling pad, and even putting in a little bit of a geotextile, similar to what we see with the GRS IBS abutment structures out there. We're reinforcing that foundation to provide additional bearing capacity. So always an option there. Our software does it automatically. It does some iterations for you and helps you kind of gauge that if you bring in your soil properties. 6.3 talks about the infill soils. Infill soils, I'm going to start with the best. If we can use all of that clean stone, we call it wall rock. We do that as the entire infill area, not just 12 inches behind, but if we can do the entire grid zone, now that creates a mass that is drainable, that consolidates well. There's a lot of reasons why we like using rock as that entire backfill material. Obviously we get back to that first point that if we have on-site soils being used, we just got to make sure everything else is being adjusted accordingly, which is, the soils and waters and stuff, again, that we're talking about. Continuing with the infill soils, coming right out of our spec book, kind of building on that, we know that unsuitable soils like those heavy clays should not be used there as well. Poorly graded sands, I mentioned that earlier. If I've got that beach sand or that sugar sand, those have a tendency to move on you, even with very minimal water being introduced. If you have that as backfill material, special considerations need to be handled. You might need to encapsulate that more with a fabric and not just use the conventional things. Obviously, expensive clays, higher plasticity index can't be used when you have that fine-grained cohesive material. A little bit of a review here again. We got that range of PI from 6 to 20 and liquid limits from 30 to 40. It can be used, but as you can see, bold and underlined, additional backfill and compaction, water management efforts need to be handled, as we discussed before when you talk about allowable soils. Okay, we talked about 6.3 one last time. Getting into suggestions. Again, wall rock is perfect. That clean stone. In CMA Allen Block, we put in this sieve analysis of this grain size distribution here. Obviously, you can see most of that is a 1 inch or a number 4, which has got some larger particle sizes. You'll see that we've got very little passing a number 200 sieve. That means it's more of that granular material, which is perfect. So take that for what it's worth. If you can use something of this material that really simplifies the installation side of it, really simplifies the design side of it, because you've got a better material. But again, getting back to one of the key advantages to a segmented retaining wall is you can use on-site soils. Just make sure you're looking at those special considerations. All right? Let's get into wall rock a little bit. That's what 6.4 is. Wall rock is used to call drain rock in the old days, but we got tired of people draining all the water to it right behind the wall, so we simply changed the term to wall rock. But it does many things for us. It does more than just drain the water. It adds weight, it adds stability, it aids in compaction. There's a lot of things. So what we do at Allen Block, we've got a general spec for it. It's a 1/4 inch to 1.5 inches is particle size, or basically 0.6 to 3.8 centimeters, but then no more than 10% passing that number 200 sieve or fine material, which means it's a wash stone. We know that at least we got to have it 12 inches behind the wall here. You might go a little bit deeper based on the type of soils you have. But if we're using that wall rock and we're capping it with our topsoils and stuff like that, best practice approach is just lay a little fabric, about 3 feet, maybe 1 meter in length, just on top here, just to kind of make sure that gravity doesn't take over and starts bringing in a lot of that topsoil to the top of it there. One other thing for wall rock, and I'm not going to get into a lot of this, I know our next month's session gets into the grid, but I mentioned the wall rock aids in compaction. So when we're talking these outside curves or radiuses, best practices is coming in with a little bit more rock in those zones because it aids in compaction there, consolidates the stone there, and we got less likelihood of the movement at those 2 points. So just keep that in mind. You'll see that in the typical details from here on out, not only from Allen Block, but a lot of the other competitive blocks out there too. But it's something that we want to start doing a little bit more here. Okay, 6.5, it really, plain and simple, quick, easy reference, websites, searchable through Google, whatever it is, soil verification. Really what it means is we want on-site soils to verify, or on-site engineers to verify the type of soils being used. Make sure it matches the design documents. You might have multiple soils. Here I got, again, in the AB walls showing 2 different soil types in the retained soil. You might have some clay material below and then moving into a fill material above or whatever. And so here you can show that. If you've got a long project, maybe a couple hundred linear feet, you might have different soil types throughout the length. So having that on-site soils engineer is important. Obviously, not every project is going to have that. If you're talking about a residential application of a 3-foot-high wall in somebody's backyard, you're probably not going to have a soils engineer out there. And so understanding the scope of work is important, but then that gets into educating, and where Allen Block comes in, we're trying to educate the contractor, making sure they realize not every soil is what they call brown. We don't care about the color per se. We want to know what type of material it is. So that's important to classify the soil. 6.6 for best practices. This gets into establishing the testing requirements. Again, coming back to the size and scope of the project, residential versus commercial, DOT, Ministry of Transportation versus a small little garden wall. We want to make sure we're putting in the type of testing requirements that is. And one of the biggest points we have under 6.6 is we want independent testing being done, but we would love that to be done and paid for by the owner or the client. Ultimately, they're paying the bill anyway, whether the contractor is securing it or the owner is directly. But we like kind of defining those roles and responsibilities. The engineers design, owners obviously are the end-all be-all, but contractors should just have to construct that wall. And so we like to try to have the independent testing hired by the owner and being part of that. And then obviously they document what's being done, keep the logs, and help the owner make that determination whether it's done properly or not. The last point under 6.6 is inspection shouldn't stop just when the wall stops. If there's any slopes above this wall, we got to make sure those slopes are being compacted at the same time, making sure they're following the same requirements, whether it's the 95% standard Proctor or modified, whatever it is, and just that the grading contractor just doesn't throw loose material above this wall. We've seen where that loose material has settled and maybe even bulged the top portion of that wall because of you got that isolated pressure on top. Okay, 6.7, we're moving right along here. 6.7 talks about facing compaction, and this is the key element. When we're talking about face operation there, a lot of people try to resist getting equipment too close to the block, and I understand why. You don't want to bulge it out, you don't want to move it, you don't want to knock it off a level, but it's so important to make sure we consolidate that material right behind the block, just before those same reasons I talked about with that down drag forces, making sure that grid stays horizontally and not getting pulled down because of settlement behind the wall. And that's where that wall rock comes into play, because if you take all that rock and you consolidate it with the plate compactor, that's going to settle up, or that's going to consolidate pretty well for you. You're not going to have those major settlements that you'll see. So we recommend a hand-operated plate compactor. On that first picture right above, that we're going to run that plate compactor right behind the wall. But you'll notice on the second course and above, we want that plate compactor right on top of the block. So we're consolidating that stone in the cores and everything else too. So that's right in our installation manuals. Whenever we do our contractor certification class, we emphasize that. I know a lot of our production partners will show that as part of the hands-on session, which is great, because seeing is believing when you're talking about that stuff. When we talk about 6-7 continuing those spacing requirements, we just got to, again, taking a page out of the spec book, we got to make sure that we're consolidating that zone. When we're using the rock, it's great. We got to make sure it's compacted to the same level of effort that everything else is. Sometimes it may be just like more of a performance, that if they are using a lot of rock, they can do a couple passes with the plate compactor in reasonable lifts, and they're set. If you've got that expansive soils that require additional compaction, maybe they got to narrow that down a little bit, because obviously you're not going to use heavy equipment. So if you've got that clay material within that first 3 or 4 feet, they might have to go down into 10 centimeters or 4-inch lifts to make sure they got adequate compaction right there at the face. But as I said, we want to make sure we're using hand-operated equipment just to make sure we're not moving those blocks around a whole lot. 6.8 is really about the lifts. And this one cannot be more black and white in our industry. NCMA, ASTO, FHWA, Allen block, regardless of the block that's being used, whether it's another segment or retaining wall, or even the big block systems out there that are wet cast, everybody knows there's limitations to how much soil can be compacted in one lift. And everybody's usually referring to an 8-inch or 20 centimeters lift maximum, no exceptions. And so that really holds true when we're talking best practices. In fact, as we just pointed out recently, if you've got poor soils, you might have to do smaller lifts to make sure you get that compaction level there. 6.9, it kind of builds off of a little bit more of our level of effort, getting back to the proctor tests being done. Best practices here refers to standard proctor. Usually about 95% of that standard proctor might be closer to a 92, 93% modified. But keep in mind, moisture density is so critical, +1 or -3, so that way we've got optimal moisture conditions all the way through. And that needs to be specified. Please, in your specifications, write in the notes, whatever it is, make sure you are calling out the level of effort. It must be 95% standard proctor. I know if you're using the Allen block specifications, it is doing that. And so that way there's no miscommunication of how compacted that soil needs to be. And if you got material above, like I said, those loadings, whether it's a highway, building, or whatever, you might call out modified, and you might even make it more stringent. And that's your prerogative as that designing engineer. The testing locations and frequency, this was interesting for us. We started going through our best practices manual and creating this in 2014, I guess, because we released it in 2015. And I got to admit, this was where a lot of us, we were silent on how often should you test? What frequency should you do? And so we started contacting some of our go-to engineers out there and guys that are in the industry. And a lot of times this is where others kind of peeked in as well. So the guys would say, yeah, it needs to be 95% standard proctor and it must be tested, but nobody really qualified what that testing requirements are. And so the contractor would have to go out there, talk to a third-party tester and say, okay, how often are you going to test this? And they would leave it up to the experience there, so that then the third-party tester, the geotech or on-site engineer would say, yep, I'm going to be out here. I'm going to do it by volume, or I might do it by lift. What we did in best practices is just give you kind of a little bit of a roadmap, maybe help you define that scope, So you can see here, we say one test every lift or 8 inches, 25 linear feet or about 7.6 meters. But you vary the distance behind the wall. You might be a foot behind or a couple feet behind the wall, might be 5 feet, 6 feet behind the wall. So you kind of over the entire backfill area, you're going to change this, but it's every lift, every 25 linear feet. But obviously, if there's a scope that works better, or there's a contractor that there's acceptance there, maybe you do less, maybe you have to do a little bit more. Again, it gets back to regional, it gets back to the scope of work. But what we're trying to do in best practices is just make sure it's being defined. And if it's being defined as part of the bid package, then again, everybody is doing it and it's part of the bid, and there's no miscommunication. So again, just helps raise the bar in our industry. The rest of this, a couple other talking points, we'll get into 611, talk about water management during construction. We know water tries to find the lowest point during construction if it rains. That can be your trench or the backfill area. So we just tell the contractors, make sure during the day, at the end of each day, you use best practices to divert the water around, whether that's with a berm or a quick swale, especially if rain is in the forecast. That way, getting to the question, if it does rain, it's going to change the plasticity index. We're going to minimize that potential. So all those activities in the design side needs to be happening in the construction side too, to minimize that potential. Step ups at the base, getting into compaction again. We're pretty good about having guys run that compactor in that trench to make sure the base is compacted nice and tight. But where we see some shortcuts or just some misses there is that, again, they try to not get too close to that block. And so we might get some consolidation problems here because they're not running that compaction equipment too close to there. And we've seen some minor settlement there. And again, any minor settlement could be a problem in the big picture. So we just try to make sure everything gets compacted throughout this. And here, again, it's easy for us to show these 90-degree bends, but let's face it, it's easier to just bring in a little bit more rock in these areas to make sure we don't have those differential problems. Right. And then one of the last ones here is similar to what we just talked about with stairs. In fact, constructing of stairs is a hot topic. We did a ABU online for contractors a couple months ago, and it was probably one of our most our well-attended sessions where we talked about stair construction. Unfortunately, the conclusion out of there's no silver bullet. Every set of steps is a little bit different, depending on the tread depth they want to do, the rise. But what I tell the guys when you talk about compaction is, again, don't get cute. It's easy to show this line art showing in 90-degree bends, but really we want to oversize the excavated amount. In fact, Rich and the guys next month are going to talk about grid. I even recommend putting a little bit of grid in this area because now that holds that entire stair area together. I call it more of a staircase instead of stair steps. And so that way we're compacting this and it holds it all together. And that's really what we're doing, is making sure we got at least 6 inches of rock underneath this, more the better, making sure it's compacted to the same requirements that everything else is. So with that, I'm kind of wrapping up chapter 6, to be honest. We had 13 different talking points. We started with the review of soil mechanics because, as you saw, that we need to identify what were allowable soils. So we know we can't overlook these. I brought it up right away. It is probably the second causing, or these two topics, soil and compaction, probably leads to the failure of walls right behind water management being the number one. But if you overestimate the soils, bad things happen. If you don't get soils properly compacted, bad things happen. So we know they're important. We know they're not only in the wall calculations, but as global stability testing is the only way we can go ahead and get the accurate numbers. But then compaction. Compaction to me is not just an installation issue. It is, to me, a design issue. We want to make sure we have everything communicated as far as expectations. What is the level of effort for the compaction, whether it's the Proctor test, and then what is the testing requirements all the way through. So with that, been at it for about 45 minutes. I'm going to open it up for questions. I know we had one question that I addressed during the session, but here's your chance to type in if something didn't make sense to you, or if you wanted me to elaborate a little bit more on, use that question. I'll monitor that as we go here. But even if you want to ask me something afterwards, I'll be following up with you with an email with some of the attachments that we had going on here. And if you've got something specific that you want to ask me at that time, feel free to send me an email back. Again, we get to do retaining walls every day, and we're happy to help. But as we wait for some questions, the last attachment that is part of this webinar is the evaluation. So if you are looking for continuing education credits, feel free to grab that evaluation and fill that out. You can go ahead and email it back to me. My email address is here, but otherwise, like I said, I will be sending you an email, and that evaluation will be attached to that as well. We did have another question pop up. It says, how do you know what the optimum moisture content is, and how do you get the soil to that content in situ? Yeah, the optimum moisture is usually a couple different ways. We're doing a couple different tests, plasticity index and stuff like that. But when you're talking compaction, it is all that Proctor test. And so that Proctor test will give you the optimum moisture. Then you're right. Rick, you're the one asked that question. How do you make sure that soil is at that content? That's the trick. If you're on a wet condition, you've had rain for a number of weeks, they may never get to the compaction levels because the soils are just too wet. They got to let it dry out. On the flip side, if you're working with more granular material or sand or something, you may need to add water to that. And so really that comes to in situ testing. Most of you guys are aware, and maybe I should have added that, a lot of times the way they're testing the compaction is through nuclear density gauges. That is just using a nuclear gauge, driving that rod into the ground, and that's giving you in situ or actual testing results of the soil that is below that device. So then you just compare it to the optimum conditions that's being outlined in your Proctor test. So no, great question. It's kind of a 1-2 punch. The Proctor test gives you the optimum conditions. The in situ testing, like a nuclear density gauge or something like that, will give you how well you compare to that. So Rick, I hope I answered your question. If I didn't, feel free to ask a different one or elaborate that a little bit more when you get my email. Next month, I hope you guys can join us. Pretty excited for this one, to be honest. It's Chapter 7, talking about GeoGrid, whether it's the placement, the type, the manufacturing. Right now, Rich Lovedall's putting that presentation together. If you're familiar with him, he's another senior engineer, that's been with us for 18 years as well. But we're going to be joined by Mike Bernardi. And if you've heard that name, he's the engineering director at Strata Systems, been in the industry for a very long time. And he's going to be a guest speaker and talk about the manufacturing process and things to consider when you're looking at specifying the type of grid. And so he's going to build off of that. But with that, guys, I want to just thank you again for your time. Please let us know how we can help. We obviously have a lot of tools and resources that are here to help. I showed AB Walls several times. It's one of the design tools that have been modified to incorporate a lot of the best practices. If you have a copy of that and need a refresher, if you want a copy, let us know. But let us help you. I started this presentation by saying that we do retaining walls every day, and that can be fun and exciting depending on who you are. But the beautiful thing is we get to learn from a lot of different people, and we'd like to share that knowledge with you and help you with that. So again, thank you for your time. I don't see any other questions. I'm getting a few other thank yous on here. So with that, good luck out there, and let us know how we can help. I'll sign off here now, and I'll follow up with you here with an email either this afternoon or maybe tomorrow morning. So again, thank you for your time.